Welcome to Homework Lib.
So over here we have the following chemical reaction. We're going to have formic acid that in the presence of water is going to react to produce HCOO minus, the conjugate base, plus H3O plus. In this case, we're given the value for the Ka, which is 1.8 times 10 to the minus 4. Thus, the value of pKa, which is minus the logarithm of Ka, would be equal to 3.745. We are told that the initial concentration is going to be equal to 0.0112 molar. So this is a very small concentration. And we want to know what is the equilibrium concentration of the formic acid. In order to do this, we're going to start with an ice table. I'm going to write down again the chemical equation. Of course, in this case, I'm omitting the aqueous phase just to make it a little bit simpler in terms of notation, but you can add the aqueous in each of the compounds that we have here. And our ice table is going to read as follows. We're going to have an initial concentration of C0. In the case of water, it doesn't matter because it is a condensed phase, and condensed phases do not enter into equilibrium equations. Next, we're going to have initially 0 of each of these compounds. Their amount of change is going to be minus X, and plus X, respectively. So at equilibrium, we're going to have C0 minus X, and X. In this case, our value for Ka is given by the product of the concentrations of HCOO minus times the concentration of H2O plus divided by the concentration of HCOOH. Replacing the values that we found at equilibrium, this becomes X times X divided by C0 minus X. And this needs to be equal to the Ka, which is 1.8 times 10 to the minus 4. So over here we have two different options. Assume that the value of X is going to be much smaller than the value for C0, in which case C0 minus X is going to be equal to C0, or the other case is solve the quadratic expression. So I'm going to give you the result with both procedures. On the first one, our expression for Ka becomes X squared divided by C0, thus the value for X is going to be equal to the square root of Ka times C0. Replacing the values that we got from the problem is 1.8 times 10 to the minus 4 multiplied by my initial concentration, which is 0.0112 molar. The value for X, in this case we don't need to put the units, we know that the final result is going to be in molarities. So 1.8 exponential to the minus 4 times 0.0112, square root of that, we're going to get a value of X equal to 1.42 times 10 to the minus 3 molar. As you can see, if we compare this value with C0, this represents essentially 12.7% of the initial concentration. So this is not going to be accurate. That means that the approximation is not accurate enough. For this approximation to be accurate, the value for X needs to be approximately 5% of your initial concentration. So now we need to solve the quadratic expression, which reads x squared divided by C0 minus X is equal to Ka. From here we get x squared is equal to Ka times C0 minus Kax. Rearranging, we get x squared plus Ka times X minus Ka times C0 needs to be equal to 0. So this quadratic expression is going to have two different values, x1 and x2. You can solve it either on your calculator or you can employ the general formula for quadratic expressions. Right here, I'm just going to limit myself to give you the results, and they are, in this case for x1, minus 0.001527, and x2 is going to be equal to 0.00133271. So the result that is going to be correct is going to be the positive value. This is going to be 333 essentially, times 10 to the minus 3 molar. And this is going to be the best possible result. Compare this with the value that we got with our approximation, and you're going to see that this is not going to be accurate. So now the final step is going to be directly just writing down the concentration. Sorry about this. The concentration of HCOOH, which is C0 minus X, and this is going to be equal to 9 point, whoops, Ole ya. Equal to 9 point, whoops, 9.867 times 10 to the minus 3 molar. Sorry about the noise, my dog started barking. So this is going to be our final result. Thank you very much and have a good one.